Hello everyone, this is Sir Aris. Today let us talk about matrix operations. We consider this matrix equation. Um, we emphasize that when two matrices are equal, it would mean that they are identical, so the elements should be identical. Hence, this matrix equation is the set of six equations: x equals 2, y equals 3, r equals 1, s equals negative 7i, u equals negative 5, v equals 1 minus I. For this case, if we multiply a matrix by a number, um, what we do is simply multiply each element by that number. So let's see what happens in this case where you have a vector. To write this vector with components 2 and 3 along unit vectors I and j hat respectively, we can write either a column matrix or a column vector 2, 3 written in one column, or a row matrix written in one row 2, 3. This row matrix 80, this is supposed to be 80, is called the transpose of the column matrix A. So in our notation, um, take note of these three differences. A, that is simply just uh, a letter for this corresponds to a matrix. A bold-faced letter, capital letter in this, or any letter, whether capital letter or not, it corresponds to a vector, and the italicized A or italicized letter is the length of the vector A. Suppose you want a vector twice the length of A. So if it's a vector, you simply multiply each component by 2. So if you have here 2i 3j, it becomes 2 of A would be 4i plus 6j, like this. And in matrix representation, we can write um, 2a equals 2 um, 2 times 3 or 2 2 3 2 times 2 3 equals, so you 2 multiplied by 2, that's 4, 2 times 3, that's 6. Okay, or if you want to take the twice of transpose of A, that would be 2 times 2 3, so that's 2 times 2 is 4, 2 times 3 is 6. Okay, so just like here in this vector, you have 4, 6 column vector, 4, 6 row vector, the transpose of 2A. To multiply a matrix by a number, it means that every element of the matrix is multiplied by that number. So for example, here you have K multiplied by this matrix becomes Ka, Kc, Ke, Kb, Kd, Kf. Another example, if you have negative 1 half, um, 3 fourths, negative 1, negative 5 over 8, this would be equal to, so suppose we factor negative 1 over 8. So negative 1 over 8 factored out becomes 4 here. Uh, negative, so factor 1 over 8 here. There'll be a 2 in the numerator. There's a negative, so negative 6. Factor negative 1 over 8, that's 8. And here it would be 5. So you can always put that back in. You should be able to get this. There is a difference between determinants and matrices. If you multiply a matrix by a number k, it means you multiply every element by k. However, if you want to get the determinant of ka, it's not simply k times the determinant of a. What happens is that since each term will now have a k in each element, then you need to multiply um, k to the power of n on the determinant of a. for an n by n matrix. Matrices are added by adding the corresponding elements. For example, if you have 1, 3, minus 2, 4, 7, 1, you add that with 2, negative 1, 4, 3, negative 7, and negative 2. The result would simply be, so you have 1 plus 2, first row, first column, first row, second column, 3 minus 3 plus negative 1, so that's 3 minus 1, negative 2 plus 4, 4 plus 3, 7 plus negative 7, 1 plus negative 2, and this would then become 3, 2, 2, 7, 0, negative 1. Matrices that don't have the same dimensions cannot be added. How about multiplication of matrices? The product of two matrices A, B is equal to C. Um, if you have a if A, B are two-dimensional matrices, it would be written like this. So what it means is that, so here, A, B, C, D on matrix A, this is our matrix A, and this is our matrix B. B is E, F, G, H. So here in the first row, first column, you have AE plus BG. This can be derived by looking at this um, row and this column. So you multiply um, the first term on on that row and the first term on the column of the next matrix. So you have A times E, that is AE here, and B times G. So that's the BG. And that becomes the term, the sum of that becomes the term of the first row and first column of the product. The the term in the first row and the second column would be the first row on the first matrix times the corresponding, or uh, you multiply corresponding terms on the second row of the second matrix. So you have A multiplied by F, B multiplied by H. You add them, you have AF plus BH. You do the same here. In the second row, for first column, you multiply CD and EG. So you have CE plus DG. On the second row and second column, you have CF times plus DH, like this. Generally, um, if you have the element in row I and column J of the product is equal to the row I of A times the column J of B. So by this multiplication here, it means that we're doing row times column. So if the row have these elements, or these elements, the column has these elements, multiplying them means you multiply first uh, corresponding terms according to order, and then you add the terms. So in general, in terms of indices, you can write it like this. So you have here for of ith row and jth column of the product, you have AI. So you're considering only the ith um, row of the first matrix and the jth column of the second matrix, and then you just sum um, this overall, this k here. For matrices to be multiplied, the number of columns on the first matrix should be equal to the number of columns in the or number of rows in the actually number of columns of the first, yeah, the first matrix should be same with the number of rows, because if um Let's say this one has an extra row, let's say xy here. This multiplied by this would not be defined. Consider the product of A and B. So AB would be 4, 2, negative 3, 1 times 1, 5, 3, 2, 7, negative 4. Okay, multiply this um, column with this row. That becomes 4. This one is this is 2. Okay, 4 plus 2, and um, this, or you can proceed with the second column here. 5 times 4 is 20. 7 times 2 is 14. 3 times 4 is 12. Negative 4 times 2, that's negative 8. 1 times minus 3, that's negative 3. 2, so you have plus 2. 5 times negative 3, it's negative 15. 7, 1, so that's plus 7. This times this, so you have negative 9 minus 4. Okay, and AB becomes 4. By the way, this is 1. 1 times 4, 2 times 2, this is supposed to be 4. 4 plus 4, that's 8. 20 plus 14, that's 34. 12 minus 8, that's 4. Minus 3 plus 2, that's negative 1. Minus 15 plus 7, that's negative 8. Minus 9 minus 4, that's negative 13. That would be your AB. How about BA? What happens if you solve for BA? BA becomes, so B is 1, 5, 3, 2, 7, negative 4. Okay, this. Um, A is 4, 2, negative 3, 1. 4, 2, negative 3, 1. Multiply this row with this column. That would not be defined. So it means that B, it is said to be that B is not conformable with respect to A. The product AB can be found if and only if the number of elements in a row of A equals the number of elements in a column of B. So the matrices B, A, B in that order are then conformable. So for this square matrices, we want to find A, B, and BA. So AB is 3, negative 1, negative 4, 2, 5, 2, negative 7, 3. Okay. Oops. So here, this gives us 5 times 3, that's 15. So this row times this column, 5, 15 plus 7. And then this row again, this column, 6 minus 3. This times this, so that's negative 20 minus 14. And then this row, this column, you have negative 8 plus 6. And the final answer is 22, 3, negative 34, negative 2. That's your AB. Let's see what happens if you try to determine BA. BA would be, so we flip this order, so 5 minus 7, 2, 3, times 3, negative 1, negative 4, 2. this row times this column, you get 15 minus 8. Row this column, that's negative 5 plus 4. This times this, so that's negative 21 minus 12. And this row times this column, 7 plus 6. And that would be 15 minus 8 is 7. Minus 5 plus 4, that's negative 1. Negative 21 minus 12, that's negative 33. 7 plus 6 is 13. BA is this. So this BA is not equal to AB. That's in general the case. AB, or the product of matrix multiplication, is not commutative. So generally matrices do not commute. There are matrices that commute, but not all. So we define the commutator of the matrices A and B by this relation. So AB equals AB minus BA. That's the commutator of A and B. This is also the reason why A minus B times A plus B. In this case, for matrices, this will not be equal to A squared minus B squared, unlike if these are just ordinary numbers. So the actual value of A minus B for and times A plus B for matrices would be A times A minus BA plus AB plus or minus BB. Or we can also write this as A squared plus or minus B squared plus AB minus BA. So this becomes A squared minus B squared plus, using this relation, A commutator B. Okay, let's proceed. The zero or null matrix means that one means this is a matrix where all of its elements are zero. Is often abbreviated by zero. For example, if you have M equals 2, negative 4, 1, minus 2. So M squared would be 2, negative 4, 1, minus 2 times 2, negative 4, 1, minus 2. This row, this column multiply 4 minus 4. So this times this, so that's negative 8 plus 8. This times this is 2 minus 2. And this times this, finally giving us negative 4 plus 4. So this is 0, 0, 0, 0, or our M squared equal to 0. So M squared is equal to 0, but M is not equal to 0. So we have this this property that whether M be 0 or not, the square could still be 0. An identity is that uh, our identity matrix is a square matrix with every element of the main diagonal equal to 1 and all other elements equal to 0. So the notation would be, we just write it as 1 or I or U or E. I would typically write it as 1 with a double line like that. Sometimes I would add an n here, where n is the dimension of matrix. Sometimes I write n, sometimes I don't. So for a three-dimensional unit matrix, I'll write it as I3 equals 1, 0, 0, 0, 1, 0, 0, 0, 1. For a unit matrix, it would be that IA equals AI equals A. For determinants, If you want to get determinant of AB is equal to the determinant of BA, or it's also equal to determinant of A times determinant of B. Consider this matrix equation. Um, there's a matrix. This is a column matrix, another column matrix here. If you multiply the first two matrices, you get this times this. So that would be x minus z. Um, the second row would be negative 2x plus 3y. And then the third would be x minus 3y plus 2z. So that's the product of these two. On the right hand side, you have 5, 1, negative 10. So again, matrices are equal if the elements are equal. So x minus z equals to 5. So you can write this as a um, set of equations. X minus z equals 5. Negative 2x plus 3y equals 1. And x minus 3y um, plus 2z 2z equals negative 10. Okay, this is a set of equations where there are three variables. So using letters to represent the matrices, we call this M, we call this R, we call this K. Okay, so you have M, R, and K. We can write M times R, matrices M times R equals K. Or in index notation, we have this. Also, if you have, suppose, there is a matrix such that M minus 1 times M equals a unit matrix of whatever dimension. The dimensionality is the same with the dimension of M and M to the negative 1. So if this happens, then it means that if you multiply this by M minus 1, so if M minus 1 times M R, you multiply also the right side M minus 1 K. Multiplication is both would be both here from the left side because matrix multiplication is not uh, commutative, does not follow the commutative property. So if you multiply from the left side on the other side of the equation, you also multiply from the left side. This is 1, which means that if you know m to the negative 1, you can find r. If you just multiply m to the minus 1 by k. This m minus 1 is called the inverse of a matrix. We define it by, say, it's m minus 1, m times m minus 1, or m minus 1 times m. They are both equal to the unit matrix. Um, Only square matrices have inverses. Also, some square matrices do not have inverses. It would be good to know what is um, the condition for a matrix to have an inverse. Um, if this is true, then it means that if you take the determinant of m minus 1 times m, that should be equal to the determinant of the unit matrix, which is 1. Okay, so if, for example, for a um, three-dimensional unit matrix, we 1 times 1 times 1, so that would be 1. So here, using a property that I have mentioned just a while ago, here this one, determinant AB equals determinant A times determinant B. So here, be determinant of M inverse times determinant of M, and that's equal to 1. It means that both of them should not be 0. So this is not 0, this is not 0. We don't know what is the inverse. We're more interested in M. So it means that the determinant of M should not be equal to 0. Uh, for M to have an inverse. If a matrix has an inverse, we say that it is invertible. If it doesn't have an inverse, it is called singular. To find the inverse of M, we need a cofactor. We've discussed this previously. Recall that the cofactor Cij of the element Mij in row I and column J is a number equal to -1 I plus j times the value of the determinant remaining when we cross off row I and column J. Um, to demonstrate, maybe we'll use this example. Okay, so suppose C is a matrix whose elements are Cij, so the cofactor. Ct is the transpose of C. We interchange the rows and the columns. The inverse of M would be 1 over determinant of M times Ct. The determinant of M can be determined by the cofactors also. So for example, let's find the inverse of this matrix. So the determinant can be found by the cofactors. So let's solve for the cofactors. Let's say the cofactor C11 on using or the corresponding to the first row and first column. So we cross this. Okay, by crossing this, we find 3 0 and minus 3 2. So we take 3 0 minus 3 2. The times -1 to the power of 1 plus 1, so that's 1. The answer is 6. Now, how about C12? C12, if you use this expression, that's 1 plus 2, that's 3, -1 to the power of 3, it's -1. So there's a -1 here, okay, times, so again, we cross this out, we get -2, 2, 0, 1. -2, 0, 1, 2, which is -2 times 2, that's 4, -4 times -1, that's 4. C13, we derive by crossing this out. You have -2, -3, 3, and 1. -1 to the power of 1 plus 3 is +1. So we ignore that. This would be -2 times -3, that's 6, minus 3, that's 3. We do the same thing for the other terms of the cofactor matrix. So C21 is 3. I'll just write it directly. C2 um, 2 is 3. C23 equals 3. C31 is 3. C32 is 2. C33 is 3. So the cofactor matrix is then 6, 4, 3, 3, 3, 3, 3, 2, 3. Okay. Now the determinant can be determined by using any three um, rows or columns of this matrix. You just multiply them or to the term corresponding to one row or one column of this matrix. For example, if you want to use the first row, you just multiply 6 by 1 plus 4 times 0 plus 3 times -1. So that would be 6. Determinant of m would be 6 minus 3. That's 3. C transpose is, so you switch the rows and columns, so it becomes 643 in the first row, it becomes 643 in the first column, 333 second row, that's 333 in the second column, 323 last row becomes 323 in the last column. So finally, that gives us M inverse, which is 1 over determinant of M times C transpose. So this is 1/3, 6, 3, 3, 4, 3, 2, 3, 3, 3. Okay. Matrices. There are also rotation matrices that would relate a vector and a rotated vector. Suppose we rotate it by an angle theta. If R is the column matrix corresponding to R, so R would be X, Y. R is capital letter R is capital letter X, capital letter Y. There would be a matrix M, a rotation matrix M, equal to this matrix, so that if you operate that, you get the expressions of for the components of capital letter I in terms of components of small letter R, okay, small letter X and Y. This is the rotation matrix, which we will not derive, but we'll use this. Suppose we want to rotate uh, this capital letter R by phi to get R prime. So in matrix uh, notation, you have R prime equals M prime times R, where M prime is this matrix. And this would be, so if you want to rotate R directly to R prime, you would then simply have an expression for R prime. You replace R by the R we have here, which is M times R, and you get M prime times M. This would now be the rotation matrix for going from R, small letter R, to capital letter R prime. If we evaluate M prime M, that would be, so M prime is cosine phi sine phi negative sine phi cosine phi. M would be almost the same form, but phi replaced by theta. Cosine theta sine theta negative sine theta cosine theta. Multiply using matrix multiplication. This would be cosine phi cosine theta minus sine phi, this one, sine theta. This and this, you have sine phi cosine theta plus cosine phi sine of theta. This and this, you have cosine phi or negative sine of theta minus sine phi cosine theta. And finally, this and this, negative sine phi sine theta plus cosine phi cosine of theta. Simplify, so this is just trigonometric identities. Cosine phi cosine theta minus sine phi sine theta, that's equal to cosine of phi plus theta. This is just sine of phi plus theta. Okay, here this one is negative of sine sine cosine, so that's sine of phi plus theta. Here sine cosine cosine, that would be cosine of phi plus theta. And what we observe is that this rotation matrix M prime M is just the rotation matrices that we use, except that the angle is phi plus theta. Here the angle is theta, here it's phi. If we go directly from small letter r to capital letter R prime, we just use an angle theta plus phi. And finally, matrices can be used in functions. So you have a function fa of a matrix 3 minus 2a squared minus a cubed minus 5a4 plus a6, where a is this. We simplify first some terms. For example, you want to know a squared. A squared is I squared of 2 negative square root of 2 minus 1 times 1 square root of 2 negative square root of 2 minus 1. This row times this column, that would be 1 minus 2. This row and this column, that's negative square root of 2 plus square root of 2. Um, this times this, so that's square root of 2 minus square root of 2 again. Um, Square root of 2 minus square root of 2. This is minus square root of 2 plus square root of 2. This and this, that's negative 2 plus 1 equals negative 1, 0, 0 minus 1, or that a squared equals negative of um, identity or unit matrix in 2 dimensions. So you can write 2 here, or you can also omit that. I will omit that. So here, um, that's a squared. For a cube, you just then multiply this by a. That would be negative a. A fourth, you multiply this again by a. That would be negative of negative 1. So that's 1. A5 would be this times a. So we go back to a. And then it just cycles out. So for function fa, that's 3. So by the way, if there's no matrix beside that coefficient, it is understood that it has a coefficient. It is multiplied by a unit matrix. If 2a squared minus a cubed minus 5a fourth plus a6. So we don't have a6. So a6 is simply, so we go back to um, a times a, that's negative 1. Okay, so it's 3. 1 minus 2 times negative 1 minus a3 is negative a minus 5 1 plus a6 is negative 1. Okay, so 3 plus 2, that's 6. That's 5. 3 plus 2 is 5. Or let me write it again. 3 plus 2 plus a minus 5 minus 1. So 3 plus 2 is 5 minus 5. That cancels out. So you have a minus 1, or your fa equals a, what again is a, 1 square root of 2 negative square root of 2 negative 1 minus 1 0 0 1. That would be 1 minus 1 is 0. Square root of 2 minus 0 is square root of 2. Negative square root of 2 minus 0 is negative square root of 2. Negative 1 minus negative 1 is negative 2. So fa is 0 square root of 2 negative square root of 2 negative 2. Okay, how about g, function g? We're looking for g of a, which is e k a. K is a constant in this case. So what we can do, we use our knowledge on series. So we use Maclaurin series for this. We have 1 plus, so expand over ka, powers of ka. So 1 plus ka plus k squared a squared over 2 factorial plus k cube a cube over 3 factorial plus k fourth a fourth. This goes on, but I will include some important terms: k5 a5 or 5 factorial, and then it cycles out. Okay, we substitute terms. One here doesn't have a matrix coefficient, so it's understood that that is simply the unit matrix. Plus ka plus k squared over 2 factorial a squared is negative 1. K cube over 3 factorial a cube is negative a. Plus k fourth over 4 factorial a fourth is 1. And then k over 5 factorial a 6, it goes back to, oh no, this is 5, this is just 5. A5, it goes back to a, and so on. Okay, so our e to the power of ka is equal to this one here. Let's group terms that doesn't have a. So you have 1 minus k squared over 2 factorial 1 plus k fourth over 4 factorial unit matrix 1, and so on. There, there are terms that uh, don't have the matrix A, just a unit matrix. Also, terms that contain A, so you have Ka plus or negative minus K cube over 3 factorial A plus K5 over 5 factorial A, and so on. And this becomes 1 minus K squared over 2 factorial plus K fourth over 4 factorial, and then it goes on times identity matrix 1 plus you have k minus k cube over 3 factorial plus k5 over 5 factorial, so on, times a. This is simply a cosine k, cosine matrix or series expansion of cosine k. This one is a series expansion of sine k. So you have cosine k times unit matrix 1. This is a two-dimensional unit matrix plus sine k a. Okay. Now, this is an identity matrix of dimension 2. Let me write it here. But in all of in this part of the problem, or in this problem, all identity matrices are identity matrices of dimension 2, two-dimensional identity matrices. So this becomes cosine k times 1, 0, 0, 1 plus sine k of a, which is 1 square root of 2 negative square root of 2 minus 1. Let me check. 1 square root of 2 negative square root of 2 negative 1. Or you have cosine k 0, 0 cosine k plus sine k square root of 2 sine k negative square root of 2 sine k negative sine k. So e ka is finally cosine k plus sine k. Here you have square root of 2 sine k. This is negative square root of 2 sine k. And here cosine k minus sine k. That would be our exponential of the matrix.